All right. Well, good afternoon, everybody. Welcome to the latest IRIS webinar. This is your host, Andy Frisetto, aka the IRIS Swiss Army Knife Project Associate, working from the Incorporated Research Institutions for Seismology headquarters in Washington, D.C. For those of you who aren't familiar with IRIS, the organization, we recently turned 30 years old. We are a consortium of universities and an NSF-funded science facility that operates programs enabling Earth scientists to perform advanced research in the fields of geophysics, particularly seismology. Today's webinar is tilted. Sometimes we have research-oriented webinars showing research results. Today's is tilted more towards highlighting resources that are available to people in the community that can help reduce energy and knowledge barriers to being a successful seismologist or successful scientist. If you're interested in additional webinar resources that might be in this direction, or just curious about our webinar program in general, we have a playlist on YouTube which has a list of all the previous webinars that we've done. And so these are available. There's also some other long lectures that have been interlaced into this playlist. One thing to note, the last couple webinars haven't been uploaded yet because we've been having some compatibility issues in YouTube. So if you're missing one that you looked for, you saw on email, but you haven't seen up on this list, we're working on it, and we'll try to get those uploaded all within the next couple weeks. Have to learn to do some format conversions and video editing here. So just some ground rules for the webinar process. The only people you're going to hear today are myself and Lars and Peter, our two presenters. And if you have a comment or question to any of us as the webinar is going on, what you should do is I have a screen grab here of what is floating on your desktop, or some version of this is your webinar control panel. So if you go down to the question box, you can actually type in a question to me, and I will see that coming through on my end, and then at the end I can direct those questions to Peter and or Lars. So that's how we'll handle questions. If somebody asks a question that's already been asked and I just haven't voiced it to the group yet, I'll probably try to condense similar questions into one. And I'll let you know that if I've gotten your question and I'm going to ask one before it. What I'll do is when I ask the questions, I'm going to read your name and question to the speaker as well. And then this is an important technical note. A couple times the webinar has crashed due to internet issues. If that happens, it's possible to reboot it. All we need to do is go back to the registration email that you received when you signed up for this and click the same link that brought you to this today, and that should bring the webinar back up within a minute or two. The other thing that helps is to know if there are groups out there that are watching this. What I can only see on my panel are the individual people that have logged in, but if you're sitting in a seminar room somewhere with half a dozen folks watching this, it helps for me to know just who exactly our audience is. So if you want to either message that to me in the chat or question box, or send me an email note after this, I'd really appreciate that. So before I turn it over to the speakers, we've been doing recently some what I call IRIS news items, just short briefings on things that folks may be interested in hearing a little bit more about. And so I wanted to do today's on the redeployment of the USArray transportable array to Alaska. So this is something that's been in the works for a couple years with test stations, and we are wrapping up a summer field season where full-on TA stations were deployed, as well as existing stations, namely the Alaska Earthquake Center's seismic network, have been upgraded. So what I want to draw your attention to is this map that I'll drag into the middle of the screen. Maybe I'll even enlarge that a little bit. So this is basically the current state as of the end of September of what the Alaska TA looks like. And most of these stations are still notional. They're either permitted, reconned, or identified via satellite imagery. And so those are the circles. So you get a sense for for what has been is in various stages of scouting, but does not actually have a seismometer there yet. The blue stations are existing sites that are current networks that are operating in Alaska, and you can see those are mostly concentrated in the south central wedge of the state. And so these are sites that will likely contribute to the TA's footprint. We may be working with the operators to do some basic upgrades to some of those sites, but by and large, those sites are already there and operating. And then the red triangles are sites that we've worked with operators already. This is the Alaska Earthquake Center to upgrade this summer. And then the red circles are stations that have actually been brand new seismometers installed that have never been, there's never been seismic equipment operating in those areas before. So this is an effort that's going to be ramping up over the next couple years. But I wanted to point people towards this update. And then if you have any additional questions, you can consult this website here, usra.org/Alaska. That has information that was up to date at the beginning of the summer. When I get some time this fall, I will probably refresh it with the new version of the map, as well as maybe some current station counts and news items pertaining to the work this summer. But I just wanted to let people know that it's coming along. It is these stations are available to do science with under the virtual network code _US-TA on the IRIS.DMC's webpage. So if you have any more questions about this, you're welcome to email me. You're welcome to consult the website. And without further ado, I will turn over the webinar to our two speakers. And so just to introduce them briefly, our presenters today are Lars Ottemoller, Professor of Seismology at the University of Bergen in Norway, and Peter Voss, who is a staff seismologist at the Geological Survey of Denmark and Greenland. And what's nice to have Peter and Lars here today is that they were actually colleagues of mine when I did my postdoc in Scandinavia several years ago. And it's fun to see them presenting on Seisan, because that's a data processing software that I used quite a bit during my postdoc, and I would say that I'm a pretty satisfied customer. So without further ado, I will turn it over first to Lars, who will start off on today's webinar, the Seisan Earthquake Analysis Software. So Lars, I'm going to send you a screen sharing invitation. And your audio is going to hiccup, and it should be back in, okay, it should be back now.
Is that all right, Andy? Can I start?
That looks great. Go for it.
Okay. Well, thanks a lot for the first of all for the invitation and the nice introduction. So I wish to talk about the Seisan earthquake analysis software today. And as Andy mentioned, it will be myself and Peter Voss from GEOS in Denmark who will be giving this webinar today. We have got Jens Havskov as a co-author of this presentation. Jens is actually teaching today a Seisan course in Colombia, which is why he cannot be with us. We're hoping that he could have actually contributed. Jens is actually the one that started Seisan quite some time ago, as we'll see, more than actually 2 decades. So we might call him the father of Seisan. At the start, I would also like to acknowledge the contribution that has been made over many years by others. The software is not all written by us, but there's many different people that have contributed over the years. So thanks to those guys. In addition, we have quite a lot of users, and they're normally pretty good in finding bugs, and they report these back to us, and that helps a lot to improve the software. So thanks to those users as well. Just to give a quick outline what this talk will be about, we're actually unaware on who is listening to this webinar, but what we'd like to try to give is an impression of how Seisan works. So to give people a real feeling what it looks like and what it can do. So we'll not really boast about the bells and whistles the software might have, but really look at some of the basics. So we'll start by giving an overview and some background material to start with. We'll then quickly get into data processing and focus on a local earthquake where we show data processing both through slides as well as illustrating how the software works based on my computer. So I hope that's going to work. We'll then pass the show to Peter, who will show some of the catalog work, which will be done with the Seisan Explorer. And towards the end, I will come back and also show data processing that can be done with global data. Seisan works both with local, regional, and teleseismic or global data. So we'll show a little bit of the differences, and we'll have some concluding remarks towards the end. So to start with, we might want to give some kind of definition what Seisan actually is, and I'll read it out. Seisan we would define as a system that is an interactive and efficient software package for processing of earthquake data at seismic observatories. So I think the emphasis here is on interactive and what we think is efficient. We sometimes get asked if Seisan does automatic processing like Earthworm or Antelope or Seiscom do, and that is not the case. So Seisan is really an interactive tool. It has got a little bit of offline automated processing, but the focus really is on interactive data processing. And we should mention that Seisan consists of many different small programs that have been put together into this one single package. And Seisan also has quite a clear definition of a database structure, which helps to organize the data. So what can you actually do with Seisan? The first one is pretty important, which is to import and export data. That's obviously something we have to do. And there's many different sources for seismic data. You might have a data logger, you might have a processing system like Earthworm or Antelope. That data can be brought into Seisan. And at that point, I would actually switch and show you a little bit of what the software looks like by bringing up an example. I have this terminal here, and I will log into our Linux server system. And what we can do in Seisan, we can actually plot and process data from a Seiscom or a BUD archive right away. So I will do that by starting the plotting program in Seisan, which is called multplot. I say that I would like to plot data from archive. I've done some setup in the background, which you don't see right now, but I will select a date, which is 30th of September at a time of 10:50. Where I know that a small earthquake had occurred in Norway. I put in 20 minutes for the duration of my signal. I get a plot like this where I can now select different channels. And what I might do is that I just decide to take all the vertical channels. So this is a dialog that I get with every time I start plotting something in Seisan. It starts by asking me which channels would I actually like to see. Then I select that I would like to get the data in multi-trace mode. Now I'm looking at 20 minutes of data. You see the plot came up quite fast, and I'm looking at data from the Seiscom archive that we're running here for the Norwegian National Seismic Network. Looking at these 20 minutes, I can apply different filters. Activating my menu up here, I can, for example, filter this 1 to 5 Hertz and replot. I can quickly see that I'm dealing with a seismic event. I can try a different filter, and I'm quite having some experience. I will quickly think that this must be a local event, and what I would do next is I would take this data out of the Seiscom archive and enter it into the Seisan database, and then start with the data processing. This was just to illustrate how quick it is actually to inspect data from a Seiscom or BUD archive. I'll close this down again and continue with the presentation, which we have here to tell you more about what you can do with Seisan. So we have the import-export. We can store data. We've got certain ways of organizing the data, both parametric and waveform data. This can be a good starting point for somebody doing research work. But most important is what we have written here as the observatory routine. So these are the basic things that we have to be able to do, which includes the analysis of earthquake data. So we've got signal processing tasks like filtering, we've got phase identification, correction for instrumentation, all those type of things. We then have computation of earthquake parameters. Typically, we're interested in location of earthquakes and their magnitude. So these are fairly basic parameters. We can do fault plane solution using a number of different tools. We've got FolkMag, for example. We've got Hash, FPFIT, a number of different tools that have been integrated with Seisan. We are able to do seismicity maps. Again, we have a number of different programs to do that. Very popular, of course, is to use Google Earth or Google Maps for that purpose. We're able to produce bulletins, and we also have tools for doing catalog search, which is quite important for many of the things we're doing. In addition, Seisan can be used as a research platform, and we've got a number of additional programs which are not really just routine, but more focused towards doing basic research work. This brings us to this slide on slightly more advanced things in Seisan. You can see there's a few dots at the bottom, so there's more than what is on this slide. But what we can do is prepare data for travel time inversion. We have links to Wellest and simul pairs. We can compute relative times using cross-correlation and produce input for HypoDD. We have detection of events in continuous data. That, for example, could run on a BUT archive. We've got implementation of moment tensor inversion at regional distances using the Jagger code. We can compute noise levels and make PDF plots and calculate spectrograms. We've got tools for crustal Q inversion. We've got another program for magnitude scale inversion. And there's a few more tools like that, which can be a good starting point for somebody starting in research. Now, a little bit more about the background. Now, we've just told you what Seisan can do, but let's tell you a little bit about background as well. Development of Seisan started in the late 80s, and it was Jens Havskov at the time who took the initiative. He had just started coming to Norway, and people started operating digital seismic stations. There was not that much software around in those days, and quickly became clear that they wished to develop software for the system they had. That was the starting point, and over a few years, Seisan developed further into a package that was distributed and became useful for others. So this thought of developing software that can be used by others was there right from the start. Peter and I were not there at the time, but we joined sometime later. We mentioned that there has been a large number of software contributors, so different programs and many different tools have been implemented over the years. We've seen steady improvements. We're now at version 10.2 of the software. Basics are unchanged. So there's many basic things in Seisan which were defined at the start, and still many things work in that similar fashion. That means somebody that knew Seisan 10 or 20 years ago would still be able to operate it nowadays. Quite important, the different operating systems that we support. We have got Microsoft Windows, which is a preferred system by many people. Personally, we prefer to work on Linux because it makes things a bit easier. But Seisan works on these two systems as well as macOS and Solaris, and it works in a very similar way. So being able to operate Seisan on one of the systems, you can quickly switch to another system as well. Data can be moved from one system to the other without the user having to do anything. So it's pretty straightforward. Would also like to give you a little bit of the philosophy of Seisan that may partly explain the way Seisan looks and the way it works. So we'll try to do that. So first of all, Seisan is an open source system. You get the entire source code with Seisan, which is very important because you can trace exactly what is being done, and sometimes you may have to check yourself. It is an open system, so we are not limited to data from a single manufacturer. You can really use it with any kind of system where you can extract data in some common way, I would say. We are entirely non-commercial. There's no registration fees, nothing, entirely free. I mentioned the multi-platform, so we wish to have the software running in a very similar way on many different systems. It has been important to integrate essential tools and data storage into one package, which means you do not have to go out and combine several different tools yourself. With Seisan, you have these tools ready for the basic processing right from the start. It's always been important for us to develop or provide documentation together with the software. That is sometimes the weak point of software, and it's quite a bit of work to provide decent documentation, and it is by no means perfect in Seisan, but we certainly make an effort to describe the programs that we have and give the user the documentation that is required. We provide support in a number of different ways. I will come back to that, and also provide training quite frequently. Now, who's using Seisan? you can see that we've got this little map, which is a global map. Seisan is used globally. This map is actually based on the Seisan users that are subscribing to the mailing list, and people using Gmail or Yahoo and so on. They're not showing up here, so we in fact have more users than actually shown here. But this may give some idea that we have users quite a lot in Europe, North America, very much in Central America and South America, also quite a lot in Africa and Asia. So we have a system that's really used quite globally. That is reflected by about 25% or more of the data that ends up at the ISC is arriving in Seisan format. So that's a fairly large share of data processing centers, we would think. But in terms of institutions that use Seisan, it is largely national and regional seismic networks. It is also fairly popular with volcano observatories, where the tasks of the data processing are quite similar to what we do in earthquake seismology. And we have a fairly large number of individual researchers as well that are making use of the tools we have or use Seisan to organize their data. You might thinking yourself perhaps if Seisan is a good maybe system for you. The question quickly comes to formats. We support a number of different formats, and we're also able to convert to Seisan compatible formats from a number of different manufacturer and parametric formats. So for the waveform data, what Seisan can handle directly is a native Seisan format that was developed quite some time ago. We can process mini-seed data right away, seed in the same way. Also GSE and SAC are among the formats supported directly. For the parametric data, so storage of phase times, amplitudes, location, fault plane solution, all these things, we have only the Seisan format that's supported. Again, we have conversion between different formats and Seisan, so it is possible to import and export also parametric data. Calibration information is important when processing digital data. Here we have got a Seisan format for those data, but also support for GSE response format, for SAC response, and also files that are generated out of seed volumes using the RD-seed program, what we might call RESP formatted data. I briefly mentioned training and support. We have fairly regular courses and workshops which are done by University of Bergen, but others as well, such as the course that is given by Jens in Colombia as part of a GFZ training course just now. We've got the software manual, which I already explained, but important to mention that we have a training document, a fairly substantial piece of document of tens of pages, giving detailed exercises, how the software is used, which comes with a data set of sample data. So the sample data and the training document go together. We also recently started to have a tutorial which in detail explains what you see on the screen, so things are labeled and you can follow what is done in the data processing. And finally, there is a mailing list to which anybody can subscribe. People on the mailing list provide answers to other users, and fairly regularly users put questions onto this mailing list, and we try to address those questions as fast as we can. There's some comments from our perspective. We can't really tell you why people wouldn't like Seisan. We can have some ideas, but these are some points that, in our opinion, might have for liking Seisan. And these are that it works on small Linux and Windows systems. So on a simple laptop, Seisan will be working perfectly well. This can be either Windows or Mac or Linux. The emphasis in Seisan has been on producing a system that is quite efficient in the data processing. So in our demonstration, you might see that it doesn't take too many mouse clicks to do simple things. So for example, picking phases is obviously something that you have to get used to within any software, but we think it's made such that it's actually very efficient. So working in Seisan through relatively large data sets can be done in a fairly easy way. Open source is very important. Any user should be able to see what they're doing and what is hidden behind the programs. It is free. People like that, of course. We're flexible with formats, which is important. We have the support and the manual. So these are some of the reasons why people may like it. I would now like to jump more into the data processing and come with a few examples of what Seisan looks like to give you a real feeling. The slides that I'm showing are part of the new manual for seismological observatory practice, which was recently released. So we're asked to provide what is called information sheet. This information sheet 11.7, which demonstrates how data processing is done in Seisan. So you may like to go to the data to the information sheet part of the MSOP as well if you would like to see a little bit more information. So I would like to start with the analysis of a local earthquake that occurred in Norway back in 2012. This is a magnitude 3.4 earthquake. There's nothing very special about it. So would use it as one of the standard examples that we can have to illustrate how the data processing works. I will start by showing you seismogram plots just on the regular slides as part of the presentation. But at some point, I will jump back into the software and also illustrate how things really work. So plotting up a file like this from the database means that somebody has inserted or added this particular file to the database. I get to see a number of different traces. On the left, we have the labeling of the traces using the SCNL code, so station, network, location, and component, location, and network. And then we've got the different traces. The data at the start is unfiltered. I may be able to guess that I'm dealing with a local earthquake, but normally we would zoom in and do some filtering, like I showed you at the very start, to show what this really is. It could have been a teleseismic earthquake, a regional earthquake, or whatever, and my data processing may depend on what type of event I have. So this would be my starting point. On my next slide, I have filtered the data. I've applied a bandpass filter that is between 2 and 8 Hertz. In Seisan, we have got one standard filter, which is the Butterworth bandpass type filter. But I can of course select what frequencies I would like to use for my filter. So applying a filter like this for a small local earthquake, I quickly get to see P&S on a number of the stations, and I can be quite sure that I am dealing with a local earthquake indeed. So having found that, I can start with the data processing, and in Seisan I can toggle between a multi-trace mode, which you're seeing now, and a single trace mode. We often do much of the phase picking in the single trace mode, like you're seeing here. So on this trace, you see a P phase that has been identified. I'm dealing with the background noise at the start. Then obviously something changes in the signal. This would be obviously my P arrival. A P phase is picked by choosing one of the numbers that you see up here on the keyboard. So I practically just put my mouse pointer here, and in this case I press number 2 and I get a phase pick like this. So it's very easy to make phase picks. On this slide you see that I have zoomed in even further. So my time scale here at the bottom now is 1 second from 44 to 45. I've zoomed in quite a lot because I would like to pick a polarity, which has been done here. So I can use the same program to pick a polarity. That is done by putting the pointer fairly high up on the trace and doing my phase pick as I had just explained. So in this case, very obviously, I'm dealing with an upward motion corresponding to a compression. Anything I do in the program gets stored in the database automatically. So as a user, you just do this job, the database does all the recording, and later you can make use of the parameters that are stored in the database to calculate magnitude and location, for example. Now here I have got the 3 traces for one particular station, ASK. I'm looking at vertical, north, south, and east component. I've done the PPIC previously on the vertical channel. I've done an S reading here on one of the horizontal channels. What else has to be done? We have to pick an amplitude, which we do by correcting for the instrumentation and applying simulation of a Wood-Anderson seismograph, which is the standard in Seisan to calculate local magnitudes. You see that I've got a window here. At the bottom, the Wood-Anderson simulation is displayed. And then I've got a routine that automatically reads the amplitude on this trace. So simply press Shift A, and this amplitude will be stored together with my other data. So these would be the basic parameters and measurements that I make, PS and the amplitude. Now I've got a different station. I can see P and S has been read here already, but I would like to jump back into the demonstration. So I'll close down PowerPoint for a short moment, and I get onto my desktop, and this time I bring up a program which is called the Seisan Explorer, which Peter will demonstrate in detail. I've got a couple of earthquakes here, and I will just very quickly start the plotting. So I get to see all the traces. You can see the data processing that has been done before. It is this station that I wanted to look at, so I can select traces, I can replot, I can zoom into this into the seismograms from this particular station. To make phase picks, I can do it in this multi-trace mode. So I would zoom in and I make the phase pick by putting my pointer here and pressing the number 2 on my keyboard, which places a phase here. So that would be probably accurate enough for this P arrival. I would similarly look at the horizontal channel and try to see the start of my S, which I normally identify on the horizontal channels like this east-west component. So I would press 8 in this case for my S arrival. The other thing that I showed on the slides just now was the picking or reading of the amplitude. I do this by zooming in around my S arrival, like I've done here. Then I can open my menu, and I've got different filters for different magnitudes. For local distances, I use the word Anderson. I apply the filter around my S signal. I've done this on the vertical component. Then I press Shift A, and I get my amplitude read and picked on the bottom trace. I've got 6,000 nanometers, and I can see my period is 0.1 second. This information gets stored with my data. So in the same way, I would process all my stations, and at the end, I would go back to my Seisan Explorer. Here I can have functions like editing my file. Here you can see at this moment all the different parameters that I've stored. You can see the phase picks that I just made here are ending up at the bottom. This is one thing I wanted to show you. I can also right-click and say that I would like to locate this event. This brings up the standard location program hypercenter that we use in Seisan. And without getting too much into the details, I can see all the different stations and phases that are read, so S, P, and so on. And I can see the time difference between the observed travel time and the calculated travel time. Difference gives me the residual. So these are parameters that I look for when I revise my location, and I might adjust picks at different stations in a similar way. So much for the demonstration at this stage. I'm jumping back into my slides. Just a few more slides before I pass you over to Peter. So Peter, don't sleep. This is the station DOMB, where I'm looking at 3 component data. This is a broadband station. I'm looking at unfiltered data. I can filter the traces with a bandpass 3 to 8 Hertz. This is what the result looks like. I already made some phase picks here. So I've got a P, which is the first arriving P. This will be a PN at this distance, and I've got a secondary P arrival, which can be shown to be PG. So in Seisan, I can read both P as a first arrival and PG, which is indicated here. Similarly, I can see an S arrival and an SG, which you can clearly see there. There's another station at a slightly shorter distance. Again, I can identify a very clear first P and a PG. I can also see an SG, but I can probably not identify an SN in this case. In this case, in Seisan, we just have to make sure that the secondary S arrival is read as an SG and not as SN. So I continue like that for all my stations. At the end, I can look at all the traces using my multi-trace plot, which is done here. I can see all the phases, and we often do this to check the consistency of our different phases. I can do simple things like plotting Bordati diagrams, which you see at the top here. Phases PN and SN that correspond, or PG and SG should be lying along this line, as it is shown here. I could identify outliers and use that to verify my picks. Similarly, I can make travel time plots and try to look for picks that are not lying on my travel time curves. Another feature that I would like to mention is the reading of source parameters. So here I've calculated at the bottom a source displacement spectrum. So in that process, I correct for attenuation and geometrical spreading as well as the instrumentation. So the time window for my calculation is shown here by these black solid lines. So I get my source spectrum, and then we've got an automatic fitting routine that would adjust the seismic moment and corner frequency using a Bruin spectrum, and I can calculate parameters like the seismic moment, stress drop, source radius, and moment magnitude. This was one example. I do that for a number of stations. Here's a different station. Again, all these parameters are stored together with my phase readings and later on my location. So this is what we call parametric data. Everything ends up in the database and gets used when you relocate the event. I mentioned that we have tools to take out the data and plot it on maps. Here you can see that the location is taken to Google Earth together with location of the different stations, color-coded, showing the different residual. So yellow is a higher residual than the green colors. Red colors might be seen as well if you have fairly large residuals. And I can plot my arrow ellipse as is seen here as well. So we use that to get an idea of the station coverage and perhaps look at particular station, double check that the phases are actually okay. So this is very closely integrated with the Seisan Explorer that Peter will present next with location program and the phase picking with the mulplot plotting tool. So here I would like to leave for some while and pass you over to Peter.
Well, thank you, Lars. And I'll now try to show you all how to use Seisan Explorer. Seisan Explorer is a graphical user interface that we have built on top of the Seisan library. It's only been developed for a few years now. So you should now all see Seisan Explorer. And when you open up Seisan Explorer, you will have a log window giving you the log of the work you're doing, and then you have the event list. Now it's empty, like the one Lars showed you just before.
So 1 second, Peter. I think I need to share over to your screen, right?
Okay, sorry.
Yeah, no problem. Here, so let me do that, and your audio is probably going to hiccup for a second.
Yeah.
Okay, good. I can see it.
Okay, so once again, on my Windows system here, I'll start up Seisan Explorer. This is the icon I have down here for Seisan Explorer on a Windows machine. What you see when you power up Seisan Explorer is first you have a log tab where you get log messages from when you're running Seisan Explorer, like who is the operator ID, in this case it's me, and where is your home directory, and where is your working directory. And then you have a tab like Lars showed you before where you will have all your events. As I said, we have just developed Seisan Explorer for the last few years, and it's been tested intensively on Windows and Linux, but we hope it will work on Mac as well. I'm not so sure it's going to work on Solaris like the classical Seisan. But anyway, the options you have in Seisan Explorer is like you have files, and then in the files you can select different types of Seisan databases. So you can open default databases. It's a setup you do in Seisan for this is the database I work with always, and then you can have your database in a local folder. You can select different databases from your database catalogs, and you can have Seisan catalog file, index files, and so on. You can then close your database afterwards, and you can edit the different Seisan input parameter files. You can set. You can set the time window you're working on, and you can change your working directories, and there are some configurations. Then you have an event list that's basically you can filter on your catalog. You have different kind of functions. I'll return to that, and then just an about where you can see which the most important here is what version of Seisan Explorer you're working on at the moment. So I'll start by showing you how to open up a database from my folder of databases, and I'll go into this is my folder that comes when you install Seisan. You'll get all these folders, and in one of them that's called the layer, you will have your databases. So databases in Seisan is basically small ASCII files. So I'll go and it's Oh, sorry. I need to find a folder with some data in. Let's go back here. Oh, so anyway, you have your catalog in these folders per year and per month, but then I'll try to select this database called CMT. So it's a subset of the global CMT catalog. And I'll show you. I'll be asked what window do you want to look at. So I'll say 1975 and some starting date, and the end date is the current date. So that's today. You can see down here. And it will now load the database, and you can see down here at the bottom that it's now reading all these event files with the parameters of the earthquakes. So it should end up at 100. So when it's done, what you see here is that all the earthquakes are listed in time, and you have the lat long of the earthquakes, the depth, and you have different kinds. You have the here it says Harvard agency. You might also have gaps and what type of event you have. You have the magnitudes, the MW, you have ML, and so on. So as Lars showed you, you can open up parameters files. I'm right-clicking now, and then I can say I can edit this file. So this is the parameter file. It's basically just a header line with the location and time, and there are some magnitudes here. And in this case, we also have moment magnitudes, the moments into results from the Harvard catalog. So in this case, I saw there was also MB and MS, so I want to add those as well. So I go in and I say select columns, and then you have all the columns there. You can select the different kind of values. So I say I want to see MB and MS as well. So they are now added to my event list. You can scroll down, and then you can see all the events that has been loaded. And as I said, it was a subset of the Harvard catalog. So if I say Shift Control A, I'll mark all of them, and then I can actually go and I can plot these with Google Maps. So let's hope it works. And there you see it will open up Google Maps, and it will show you where these earthquakes are, and you can zoom in different kind of ways. And there you see this subset is all earthquakes in Chile and Peru and Bolivia in this subduction zone. Or you can just select a single one, and then you can map that as well. So now the next thing I'll show you is how this filtering works. So if you go into this set filter, this dialog box will open up, and there you can edit this filter type, and it works like this. For example, if you want to have the big earthquakes, you might set a filter where you have magnitudes above some value. So we'll say above 6. So this is now my filter. You can save this. So I'll say call it big quake, and then you can save that one for later. And you might want to put it in your working folder. Oh, sorry. So you want to now we'll create a file with this filter. I'll just call it big earthquakes and save this one. So now I have my filter, and I'll apply the filter by pressing OK. So now all these events are sorted. Now you see I only have a handful, and it's all the big ones. It says up here now you filtered it with the big quakes, and then I can take this filter off again and maybe use it at a later time. Remove the filter. The next thing I want to show you is that we have developed these functions, and there are different kind of functions for hazard work and just for reviewing your catalog. And one of them is, for example, you can plot Gutenberg-Richter relation. So you open this Gutenberg-Richter, and now you need to decide which kind of magnitude you want to use. We have something called just M, and it's like a master magnitude. It's not at it's set to just point at the moment magnitude, but you can select other magnitudes as well. So if you want to see some the Gutenberg-Richter for something else, you say replot, and it should. Oops, sorry. It will select that one instead. So we'll go to MW replot, and then you can change the intervals. Go to half, do replotting. You can show the incremental and let's say values, say plot, and you will see those on top. The next thing is you can now estimate the p-value using these points, but then you need to set a starting magnitude. You can either go up and down, or you could just type in 6, for example, and you want to go. You might want to go up to 8 or something like that. You click the values you want to use. You say replot, and now up here you see with these points it has estimated the A and B values. So that's quite easy. There's another option down here in the function, that is you can print. So you can take this image here and then you can send it to a PDF or PostScript or PNG file, but just printing directly, and it will be saved in your working folder. Another function I can show you is we can plot magnitudes against magnitudes, and what it means is that you might want to see how the movement is plotting against the MB. So it just goes through the database and takes all the MWs and all the MBs that are on the same quick and then plot it here, so you have movement on one axis and MB on the other one. You might want to see a legend and see how many counts there are for each pair, so it will be colored now. And you see for the MB there's some saturation above 6, as one would expect. So that's another function, and here again you can also print, and this means that you can set the size of your print by pixel size. Okay, there's another function. For example, you can export it to an ASCII table if you want to plot it with something else, or bring it into Excel, for example. You can select different lat long values, for example, or you might want to choose the depth, or you want to take out the magnitude, for example. Then you just say check out these values, and then you can select the separator, and then you press export, and you get an ASCII file that you can easily load into Excel, for example. So when you're done working with your database, you just close it if you want to jump into some other database. So now we just close the database. Yes, thank you. And then we might want to look at some other database. You say load the database, go into your IRIS folder. Now we have a folder with a bit more data for statistical work. So this one is going back to a bit longer. So I'm loading in this new database. No, that is. So in this case, I just loaded in a lot of old earthquakes. I only have the time and I only have the magnitude here. So this, just to illustrate another function, is called the completeness check. So if I press the completeness check, it will plot over here the number of increasing number of earthquakes over time. So to check the completeness of your catalog, you will see that this line represents all earthquakes from 7 to 8, and the next one is from 6 to 7, and then from 5 to 6. And you can change the intervals by editing these values, and you can change the magnitude you want to look at. And the way to store the completeness is that you need to find the time that this curve is steady. So in this case, this magnitude interval seems to be starting from 1830. So you might need to enter here 1830. And for the other one, it seems to be a bit later, like 1855. I presume. Then when you do replotting, you see these points are jumping down to this starting time of completeness for the magnitude intervals, and you can do the same with all of these. And when every time you do replotting, these values will be saved in an ASCII file, and then it can be used for other statistical use. So another kind of, there's other functions like you can plot the Poisson distribution. It will look like this. So it will test your database and the number of earthquakes in yearly intervals against the theoretical Poisson distribution. That's another way of testing the data. And then there's some other, you can have time of day distribution and different other functions. We also have these sample functions, and they are just quite simple. It will just show you values, but the idea of these sample functions is that if you want to add some of your own functions, you can modify the C++ code of these functions and then get the output that you want for yourself. The software is written in Qt, but it's mainly, it looks very much like C++. And there's the other test function. It just has a graph in, and then you can replace it with whatever you want. So in this log window, you now have the logging of what you did. We try to store as much information as you want, but what you can do here is you can clear it, but you can also save your log. So if you have done something that you want to repeat it, sometimes you can save the log and use this log file next time you want to do the same kind of processing. So I'm just as Lars showed you, just gonna look at the final database. I'm looking at a database we call test now, and every time you install Seisan, you will receive a small test data set, so there's a few events. It's called the test database, and it comes with all versions of Seisan. I'll just say 1990 here. So when you install Seisan, you will get, in the Seisan package, you will get some these two earthquakes to look at. And the idea is, with bringing these earthquakes is that you can test Seisan and see if the installation works okay. And they are just, as Lars said, when I press P, I need to set this operator again. And there you get it, you get the traces as Lars just showed you before. There's an interactive work, you can run Google Earth next to it. So if I power up my Google Earth, you can set Google to, because Seisan is reading out KML files, and then Google Earth will just automatically read these files. So I'll see if I can, when I do the location of these events. So there you see you have the arrow ellipse, and then if I go to the other one and I press L, it will locate this event. And there you see now on here over on Google Earth, it will jump to this new location and it will show you where this other event was located. So if I go back and press L and see the location, now this pointer will show where this other location was. So apparently it jumped to the other part of the world. So there's an interactive work between Google Earth and Seisan that you can use as well. Let me see if there's something else that I missed. No, it looks like I went through most of the work you can do in Seisan Explorer, and I just want to say good luck to all of you using Seisan Explorer. Thanks a lot, and back to you in Bergen, Lars.
All right, Lars, I'm going to switch the screen back over to you, so stand by for that.
Okay. Okay, I guess that's me again. Thanks a lot, Peter. We're actually in different locations, so it was interesting that we can split the webinar in this way. So it's quite impressive. What I would like to do next is go back to my presentation here and continue to show you some of the data processing. And in this case, it's not a local event, but an earthquake from Colombia, which occurred at intermediate depth of around 130 kilometers. And on my map here, you can see stations that had recorded that event. And what I had done to extract this data was that I went to IRIS and used Wilbur to produce a seed volume. And that data I took into Seisan. And that is actually something I would like to show you very briefly that works. And you're actually aware that you can plot seed volumes produced on IRIS in Seisan straight away. So let me do that, and then I will focus a little bit more on the data processing and show you a bit of the functionality we have. So as it says here, I will jump back to demonstration, and what I do is that I bring up my secure shell again, And what I got from IRIS was a file which you can see here, which is columbia.seed, and I can plot this file as it is. So this is just a simple seed volume which I'm trying to load into Seisan. It comes up here in the background. There's quite a lot of channels that I had selected for my extract. It's probably enough if we look at just a single station to start with. So select my channels and I go forward, and I have these 3 channels. So I've got a station from Germany, BFO, which has a vertical channel now at the bottom, and I've got east and north above. You can probably easily see that this looks like a fairly nice teleseismic recording. A lot of phases might be visible. The reason for using this as an example was that it's at intermediate depth, and I may be able to see some nicely recorded depth phases, which we will try to show. But at the start, again, I would like to illustrate how the data processing works. I would have a lot of different stations, normally 3-component data, and I would start by looking. This was actually not a good choice. Let me take the vertical channel. So I'm redoing this. So this is my vertical channel for this particular station, and I would try to see where the P starts. You can probably argue a little bit, but let me say that I'm convinced my P is exactly here. This is what I would do for a lot of the stations in the first round. What I then do is that I try to obtain a location, and then I can calculate synthetic arrivals, and I would go back to my seismogram to see what additional phases I can identify. But before doing that, I can already apply my amplitude reading. So I've got different choices for teleseismic events, which is the standard MB. We've also got an implementation of the JASPA recommended broadband MB. We've also got standard MS and the broadband MS. So what we might call the 4 standard magnitudes for teleseismic earthquakes are all implemented in Seisan. I'll show you very quickly how I would, for example, read a broadband magnitude for the body waves. So I would click on this box. I take a time interval around my P arrival, very clearly to see that this is my largest signal, and I use my auto amplitude to make a reading. So I get roughly 2,100 nanometers per second at a period of 3.6 seconds. Again, this is something that I would do for all my traces. This is a deep event, so I wouldn't read surface wave magnitude amplitudes. But if I had a shallow event, of course, that can be done. So this gives us some idea of what the processing looks like. I will change back into the multi-trace mode. For this event, I already should have a location, and I should be able. I actually can't do it from here. I have to go out once and go back in because I'm still plotting the data from my seed volume. I didn't put it into a database. There was one more thing that I wanted to show you here, is that I can show you what the response for this instrumentation looks like. So we have got the amplitude and phase spectrum that is taken from the RESP file. So from the seed volume, you can simply extract the RESP ASCII files. And these are automatically used by Seisan together with waveform data. Let me see, I will very quickly try to show you as well what the plotting looks like of various teleseismic calculated phases. So I go to my multi-trace mode, and here is my box for calculating arrival times. You could notice that I had to search a little moment. So this shows me the different phases, and you can see there is something indicated as PP, and a pick had previously been made at this time, so I would have a PP phase. I can also see the calculated depth phases, and on my vertical component now at the top, we can very clearly see that we have very clear phase here. To read one of these phases, I would put my pointer very close to this calculated time, but of course I have to put it on the seismogram where I see a signal, and I then simply press Shift Y, which makes the reading. So if I replot, I now have the same twice actually. So I've made my reading of the little PP phase, which then gets used by the location program and helps us to constrain the depth of the event. So this gives you some idea. We could continue for a long time, but eventually we'll run out of time. So let me go back to my presentation to show you a few more things. We'll put it on the screens. We're done with demonstration. This is seismograms we looked at. There's obviously many interesting signals that we can see on the trace. But what happens is that we read the P arrival on a number of stations. Here you can see that my traces are sorted by distance. I've got some additional phases read here already. You can see there's a PP here and an S phase and an SKS. These would be shown here. And having done my phase arrival picks, I can calculate a location. Just like for the local earthquake, we're using the hypercenter program as a default. I can see the different stations with their respective distances, and I get to see what the calculated residuals are, which we're trying to minimize when locating events. At the bottom here, you get the location, which is 1.18 latitude and minus 77.37 longitude, at a depth of 130 kilometers roughly. Now this will be actually a good estimate because we have very clear depth phases, the little PP that I mentioned. This is a diagram again to show the different phase picks we did for this particular station BFO. We had the initial P, then you see the depth phase coming in here, and I did demonstrate already how that phase pick was made. You can see that we actually zoomed in and around the little PP on this slide, which is a time interval here. That gets shown at the bottom, and my phase pick for the little PP is made there. Moving on to the next trace, this is a different station. It's a nice event. So I have PKP DF, so core phase seen as a first arrival at this distance. But I can also see a depth phase corresponding to this first arrival. So I've got a little p PKP DF, which is quite clearly seen here. So I can read these phases in Seisan, and we always recommend people also at local observatories to make use of teleseismic data, read these phases, and report them to the IC as much as it is possible. So this can be done in Seisan, but at the same time we should say that Seisan is not a perfect choice for global earthquake monitoring, but there are things that can be done, and we always encourage people to do so. Then there is one more station. It's an example of an SKS picking, which is the calculated time is here. We can make a phase pick close to that. This was partly shown to illustrate that we can rotate traces in Seisan. So here I'm looking at the vertical trace at the top, and then we've got radial and transverse components. So I've got the strongest signal for SKS due to the particle motion on SKS, and that's where I can make the picking here. This is another illustration of the amplitude readings we make. I showed this before interactively. So I've taken a time interval around the P. That is shown at the bottom here, and I apply a filter, which is for the traditional MB magnitude reading. That gets done, amplitude gets stored, and magnitude can be calculated. Just the same for the broadband magnitude, which I mentioned has been one of the recommended magnitudes by the JASPA working group on magnitudes. And there's advantages of using the broadband magnitudes for both body wave and surface wave, so that that can be nicely done using Seisan. So that probably means we are coming to an end. No more data processing, just a few concluding remarks, and then we will end once I finish, and we will be looking forward to your questions. But let me spell out some of these remarks we have. So Seisan has been a stable processing platform for more than 2 decades and is used globally. We have got new developments, partly to have a better graphical user interface. The first step on that ladder is to have the Seisan Explorer. We hope to have plotting tools, so the seismogram processing software changed to a similar graphical user interface at some point in the future as well. We think it's very important to have user support, which we're doing through mailing list, courses. Documentation for the software is very important, so anybody else writing software should always put some effort into writing documentation. And from our view, this really has helped to make Seisan quite successful. The main strength of Seisan is that the processing is quite efficient. We think that's important. there's many nice looking tools around, which in our view are looking very nice, but make data processing fairly complicated. So in Seisan, we are trying to keep things perhaps a bit simple and try to have an efficient tool. And we have combined essential tools for working with earthquake data into one package. So that has been quite important. So that means we can come to your questions. I will pass the microphone back to Andy.
All right, great. Thank you, Lars. And thank you also, Peter. That was a great presentation. It was very thoughtful, and having so many good examples for people to see, I think, is really helpful. We do have some questions, so I think maybe the best way to handle this is I'll make sure Peter's unmuted. So Peter, you're now unmuted. Lars, you're unmuted, and I guess whoever wants to handle these as I go through them, feel free to answer. First question is from Bill Harbert, and he asks, could these PowerPoint slides also be added to the excellent Seisan documentation? There was some functionality not mentioned in the excellent manual and help materials. Thank you.
Yeah, we would be very happy to do that. We previously had some presentation on Seisan, and we've now made quite a few modifications, so we're very happy to include that with the distribution. That's a very good idea. In addition, I should mention that the examples that I showed for the data processing are part of the MSOP, which can be freely accessed at the GFZ Potsdam in Germany. So all the data examples plus 2 additional examples can be found there with a lot of documentation and text as well. So that might also be a nice thing to look at.
All right, next question is from Chip Brogan, and he asks, is there any support planned for CSS 3.0 data?
Well, should I take that, Peter?
Yes, please.
Okay. Well, CSS data has been around for a long time, and we had ambition to include it at some point, but we've never done it. So it'd probably lie if I had to say that it's on our agenda to do so. But it certainly would be nice to have reading of CSS data straight into Seisan. We would also encourage people that would like to do that, perhaps to take the initiative and make the implementation of the reading and make it then available to the broader Seisan community.
All right. Next question is from George Slad and Katie Liz Anderson, who are at the Pascal Instrument Center, and they asked, what do the presenters use for the creation of RESP response files and/or dataless seed volumes?
Is that me, Peter?
Yeah, I can say when I create my RESP files, I just use a read seed. So that's a IRIS product. So you just use the read RE seed, and then you get the RESP files. It's as simple as that.
I understood the question perhaps also the other way around, how we go from Seisan to dataless seed or RESP files. The way we do that is by having a response in Seisan stored in GSE format, and then we're making use of Reinus Lehmann's code GSE to seed, which then can convert the GSE response stored in Seisan to dataless seed. So that's the sort of most direct way to do it out of Seisan. But of course, people might use other tools to keep a database of the instrumentation and have more direct ways of creating dataless seed as well.
Yes, and of course, today we just recommend people to use this excellent software called PDCC, which is also a Seisan, IRIS software. The PDCC will create dataless seed volumes for you, and it's much more accurate and much better to use on modern instruments.
Okay, I have a couple questions from Luciana Astes and Steve Jamais, which are pretty similar. They're both curious about, I guess, part one, what velocity models do you have as the defaults for teleseismic and or local regional events? And the second part of the question is, are users of Seisan able to change what model is used? Can they use their own model?
maybe I can answer. So for the teleseismic location, the default and only model we have is the JASP91 travel time model. So there is not possible to put in any other model as it is, but we are aware that we should include some of the more modern models as an alternative as well. So that's for teleseismic. For local earthquakes, the user has to supply a 1D model, and that is very easily modified together with the station file in Seisan. So there we expect the users to put in the appropriate local or regional model for their area. That is something that every Seisan user needs to be doing.
Yeah, but as a default, when you install Seisan, you'll just get the local model that they use in the University of Bergen. So if you're happy with the geology of Norway, then you can use that one.
I found the geology of Norway very interesting, so I'd be fine with that model, but yeah. Next question is from Joelle Wick, and she's curious, do you collect user usage data for Seisan users?
User usage data, that means that people would have Seisan data and would like to submit that to a broader Seisan community. Is that what is meant?
I'm not exactly sure. I suspect she's asking just in general, collecting information on how many people are using Seisan in a given year.
Okay. Well, we don't collect that information actually. We have rough ideas through the mailing list, but it actually would be quite helpful to us to have a better overview of how many people are using Seisan, where they are, what they're using for. So it is on our to-do list to actually come out and ask people to provide us more details on what they're using it for. Partly to use that to for our own case to perhaps attract additional funding for the development of Seisan.
All right. I have a question here from Glenn Thompson, and he asks, for analyzing seismic data, does Seisan do everything you need? Are there still things you ever find yourselves using SAC, OBSPy, or any MATLAB toolboxes for?
Do you want to start, Peter?
Yeah, well, it really depends. So if you want to do noise correlation, for example, you need to write your own software. If you want to look at a spectrum, for example, you might want to use some MATLAB tool for it. So of course there's a lot that cannot be done in Seisan, but for processing and locating local earthquakes, we find it quite useful in Denmark.
I think I agree with Peter that also as Seisan developers we make use of other software like SAC, for example, and SAC might have a certain strength when it comes to pre-processing of large data sets over Seisan. I think we see the strength of Seisan really with routine processing in quite an efficient way, and at the same time it's not a bad platform to jump into other software from there. So it is fairly easy if you have your data stored even for decades in Seisan to take it out, give it to somebody else who may process the data in MATLAB, cross-correlate data, do a double difference location and so on. So we have done that in the past, and it is usually a fairly quick task to take out data and give it to somebody else, or to use it yourself and use it in MATLAB or with other research applications.
All right, I have a question from Haider Dam, and he asks, is it possible to do auto-picking for teleseismic earthquakes using IRIS.edu's 91?
I would say we do not have automatic picking for teleseismic earthquakes in particular. We've got some tools for automatic picking for local seismicity, but it's probably not a strength of Seisan to do automatic picking. So we mostly the data processing is done by hand. There would obviously be nice things that can be done for teleseismic, also using cross correlation between different tracers and using some master signal. That is not something that we have implemented so far.
Okay. I have a couple questions from Chip Brogan and George Sladd that are both related to databases. So I'll start with George's, and he asks, what kind of database underlies the Seisan system, e.g., is it a relational database, is it MySQL, etc.?
Oh no, it's just a plain flat file database. So what you have in the folders underneath your database, that you have given some names. You have the folders with years, and then on that you have the 12 folders, one for each month, and then for each month in the folder there you have just a flat ASCII file. So that's a plain flat file format.
Okay, so then Chip's question relates as a follow-up to that, and he asks, is there or are there any plans to include an interface to one of these more like Oracle, MySQL, or another relational database system?
Well, if I can answer this, Lars, I mean something that has occupied our minds for some time as well. So something that we discuss from time to time. It's again not on the planned to-do list right now. I think for the future it's quite clear that eventually we probably have to go that way. But as I said, at the same time, we have not really taken steps in that direction yet. And to add a little bit to what Peter said, I mean, it sometimes in discussions with people that know more about databases than us, it's not always clear what the best solution is. So with our fairly simple approach, it becomes very easy to take data between different computers, between different platforms. So that is perhaps an advantage. On the other hand, things like searches probably are much less efficient than they would be with a database. So we kind of playing with the idea, but maybe have not been fully convinced yet that a SQL database is exactly the right answer for the typical Seisan user.
All right. I have a question here from Corey Reed, and Corey asks, how would I use this software to utilize raw mini-seed data from a temporary deployment of stations to determine local earthquake locations in depth for a local magnitude calibration study?
Well, the first step would be perhaps to identify the seismic events from the continuous mini-seed archive, and we've got tools in Seisan that can do that. So either having hourly mini-seed files or having BUT or Seiscom type archives can be used with Seisan to run simple detectors through the data, which would allow you to identify seismic events. And then it's a matter of extracting these events. We've got tools and scripts to do that. And the next step would be to find the locations. If the question was specific on mini-seed data, then we should say that mini-seed is probably the prime waveform format in Seisan. So from the data processing, then it comes to picking phases, reading amplitudes, and eventually having the inversion for the magnitude scale. So that is, I think, all the steps needed for that type of study are present in Seisan.
All right, great. Well, that is it for the questions from the audience. I didn't read all of them, but there were a lot of very thankful comments coming from people who were in attendance. Lots of thank yous, and it was very useful and great job. And I would echo those. I thought this is one of the best technical webinars we've had in a long time. So, this is the first one where we shifted back and forth between presenters, and it was seamless. So I'm pleasantly surprised by that. All right. Well, Lars and Peter, I want to thank you guys both. This was great. And, I'm assuming if folks are trying to use Seisan and have questions, that they are welcome to email you guys for sort of technical pointers.
Definitely, yeah. So it's also been a pleasure to do this webinar. It was the first time for us, so very interesting. But definitely on questions, people can take contact directly with us. Also, it is an idea to subscribe to the mailing list and put questions out to the mailing list because we have got many users that respond to questions as well, which is very nice and really nice development.
That's a good point. I had forgotten how useful the mailing list was when I was getting spun up on Seisan, because it's typically the case that if it's a question that you have, somebody else has asked it previously too. Well, great. Well, thank you guys so much. Have a great rest of the day across the Atlantic. And for the folks out there, I will do my best to have this loaded into YouTube in the next couple weeks. Like I said at the outset, we do have a couple technical hurdles we need to overcome for the way these are being received at YouTube now, but we should be able to work that out soon. So Lars and Peter, thanks again and take care. And I'll see everyone else at the next webinar. Bye-bye now.